Hello everyone, welcome to this lecture series. Today we are going to talk about surface integrals of vector fields, and we will also discuss the Stokes Theorem and Gauss Divergence Theorem. So in the last lecture we talked about the line integral of vector field, okay? And that one of the interpretations like we give is to find the work done by force field in moving the particle or object along a path from say point A to B in the region. And now surface integrals, so if you are given a vector field f, then surface integrals will give us like the amount of fluid flowing through the surface in a unit time. So we can say call the uh, amount of flux of fluid through the surface. Okay, so we can also call surface integrals as the flux integrals here. So if for example if you have water flowing perpendicular to surface, then a lot of water will flow through that surface, so the flux, okay, the amount will be large. Okay, on the other hand, if you have a flow which is parallel to surface, so water will not pass through that surface, so flux will be zero, okay, in a sense. So in that way we can define surface integrals here. So let us take the definition that if you have a vector field f, okay, so then the surface integral is given by the double integral f dot ds over the surface, okay, and which can be written as double integral of f dot n cap ds, where n cap is the outward drawn unit normal positively oriented vector to surface element ds. Okay, so if n is the unit normal, then the f dot n, f is the fluid flow, then f dot n will be the flux, okay, of fluid through the surface. Okay, and clearly we know that scalar, this dot product f dot n means the component of f in the direction normal to surface, and as we said, if fluid flow is normal to surface, then the flux will be large. Okay, so f dot n, if fluid flow is uh, parallel to surface and n cap is normal to surface, so they will become perpendicular and fluid flow will be zero. Okay, and if the quantities are in the same direction, then the flux will be positive, and if the field and normal are in opposite direction, then we will have a negative flux. Okay, the unit normal vector we said is positively oriented. So if you see some surface which is two-sided, okay, like a solid sphere, then at any point the unit normal will be there will be two normals, one which is outward. So you have a sphere, and at any point if you calculate the normal, then there will be one normal which is going to away from the sphere, and one will be the inward normal. Okay, so here unit normal is treated to be the outward drawn unit normal, and that is when we call it positively oriented. Okay, so if we make a set of all such normals, it will be one set, and all the normals which are the other side one set, so there will be two sets. Okay, so we say positively oriented if we choose the set of unit normals that point outward. Okay, and negative or oriented if we choose the set which is inward. Okay, and then we need to find out what is the ds element. Okay, so the element ds is calculated by taking projection on the plane. Okay, so we can take the projection on either the xy plane or yz plane and or zx plane, and accordingly we can have the ds element. Okay, and then we can integrate to find the flux of the field f across the surfaces. Okay, so there are two things to be calculated. If you are given a field, then we need to know what surface is there, and what is the will be the outward normal, and what will be the surface element to solve this integration. Okay, so how we can calculate this unit normal vector n and the ds element. Okay, so if you are given a surface z is equal to g function of x y. Okay, so given this surface, and say we are going to take the projection on the xy plane. Okay, so ds element will be calculated from the xy plane. Okay, so similarly you can have a projection on any other plane. Okay, so similar results will come. So this surface can be written in either this form or this form. Okay, it can be written as z minus gxy, another function, or it can be written as gxy minus z. Okay, so if I calculate a normal to the surface, so normal we know that the gradient of function is always normal to surface. Okay, so unit normal be the gradient to surface divided by its absolute value. Okay, so this will be unit normal vector. Okay, so if we calculate from z minus gxy, so it will be negative g derivative x minus negative g derivative y plus positive k divided by its absolute value. Okay, similarly if we calculate normal from here, then it will be gradient divided by length. So again we can calculate. So you can see the difference, that this unit normal is with plus k sign, this unit normal is with minus k sign. Okay, so they are at one point there are two normals. Okay, uh, one is in the towards the positive direction of k and other towards the negative direction of k. Okay, so it is not exactly perpendicular or parallel to k vector, but increasing in the direction of k, and this is in the negative k. Okay, so we have to depending upon what surface we are given, we can either use this as the unit vector or this as the unit vector, so that you have to see through the geometry. Okay, and the corresponding uh, surface element ds we have to choose from the projection in the xy plane, and so ds element will be dx dy divided by the magnitude of n dot k, where n is the either this or the second, depending upon which one is taken as the outward drawn normal. Okay, and it's a dot product with the unit vector k. Okay, and if instead of taking projection on xy plane, if you are taking projection on other plane, then this ds can be rewritten accordingly. Okay, so if you are taking projection on yz plane, then ds will be dy dz over the magnitude of unit vector n with unit vector I. Okay, or if you are taking projection on xz plane, then the ds element can be taken as dx dz over magnitude of n dot product with j. Okay, so ds can be chosen any on these three depending upon where you are taking the projection, and the unit normal vector you can choose one of them depending upon which one is giving the positive orientation, which one is in the outward unit normal direction. Okay, uh, if we are writing the surface in parametric form, say r is xi plus yj plus zk, where x, y, z are functions of uv, so the parametric form will be this, and then the unit normal vector n cap can be calculated by the cross product of ru cross rv divided by its magnitude. So again because r derivative u and r derivative v, they are tangents. Okay, uh, so the cross product is always in the normal direction, so it will be again immediately give you the normal vector, and then if we divide with the magnitude, so it will be the unit normal vector. Okay, again we have to be careful in using ru cross rv or rv cross ru, depending upon which vector will be the outward vector. Okay, so sign we may need to change once we calculate this unit vector. Say for example, say evaluate the double integral f dot ds. Okay, where you have a vector field f as yj minus zk, and s is the surface given by the paraboloid y is equal to xk plus z square which is between y is equal to 0 and y is equal to 1. Okay, and the disk x square plus z square is less than equal to 1 at y is equal to 1. Okay, so basically you have a paraboloid which is cut at by the plane y is equal to 1 into a disk. Okay, and assume S has positive orientation. Okay, so note that in this case the double integral uh, or the flux through the surface will be sum of two, because there are two surfaces, one is the paraboloid and the other is the disk. Okay, so if you look at the geometry, then you have one paraboloid surface, okay, which is y is equal to x square plus z square with y from 0 to 1, so this whole surface, and there is a y is equal to 1 plane which cuts this, so there is another surface S2. Okay, so the total flux through surface S will be sum of flux through S1, the paraboloid surface, and the flux through this surface which is S2. Okay, clearly S1 is the curved surface of paraboloid, this. Okay, and S2 we have taken as the plane surface. So we have to separately calculate the flux through S1 surface and the flux through S2 surface, and then we can add to find the total flux through the surfaces. Okay, so if we solve for S1 first, so clearly S1 is this surface. Okay, and if I have to draw a outward normal on this at any point, then you can see that this is the positive y-axis, so the outward normal is towards the negative of y-axis. Okay, so surface S1, which is y is equal to x square plus z square, we write it as x square plus z square minus y. Okay, so that the y has a negative sign, so which makes sure that the normal vector will be in the negative direction of y. Okay, so we could have also written it as y is equal to x square minus z square, but in that case normal would have been in the positive direction of y, which will be inward. Okay, so we need to find a outward normal. Okay, so we have to write this surface as x square plus z square minus y. Okay, and so we can calculate the normal vector, which will be gradient of this divided by its absolute value. Okay, so gradient h divided by the absolute value of that. So x derivative I cap, so 2x I cap, y derivative j cap, so that's minus j cap, and z derivative, okay, which is 2z times k cap, and its absolute value, which is 4x square plus 4z square plus 1 root. Okay, so clearly you can see that normal has a minus of j, so negative in the negative direction of y, so any normal you draw here, it will be in the negative direction of y. Okay, so that will be the outward normal. Okay, and for the ds element, ds1, we have to take the projection of this on the xc plane. Okay, and on the xc plane it will be a disk of unit radius. Okay, so immediately we can calculate the ds element, and then we can solve this double integral. Okay, so we have an unit vector, the field, and on S1 we said y is equal to x square plus z square is this paraboloid. Okay, so this double integral will be f dot n into ds, and ds will be dx dz over n dot j by formula. Okay, so n we have already calculated, so n dot j we can calculate, so that will be minus 1 over root factor this. Okay, so absolute value will be plus 1 by root factor, and uh, yj minus zk when dot product with n, so it will give y times the j factor dot product, so minus of y by root plus minus z times dot product with k, so 2z. Okay, so minus z into 2z, that's minus 2z square. Okay, by root factor. So immediately we can find this dot product. Okay, find this absolute value, and then we can rewrite this as a double integral. Okay, this dot product will give a root factor in denominator, and this absolute value will also give the same root factor, so that will cancel out. Okay, so we'll only get this, and uh, so this is with x and z, so we have to first eliminate y from here, and we are working on this surface, so y can be substituted as x square plus z square, so we can rewrite this as minus x square minus 3z square by substituting y as x square plus z square from surface, and then this projection is a disk, So we can easily find the limits by using transformation to polar coordinates. So x as r cos theta and z as r sin theta, and the dx dz will be Jacobian times dr d theta, and for polar Cartesian to polar we know Jacobian is r. Okay, and it's a unit disk, so radial limits are 0 to 1 and theta limits 0 to pi. Okay, so now we can integrate with r first, substitute upper limit minus lower limit, and then we can integrate with theta, substituting the upper limit and the lower limit. Okay, so the flux through the surface S1 is minus of pi. Okay, right, and uh, now on the second surface S2. Okay, on the surface S2 is y is equal to 1 plane, and the unit outward normal will be in the direction of y. So unit normal n is nothing but j cap here. Okay, so on surface S2 y is 1, and the unit outward normal is nothing but j. Okay, uh, okay, so the flux F dot ds2 will be again the field, which is yj minus zk, and dot n cap is j here. Okay, and dx dz over n dot j. Okay, so because n is j, so j dot j will be 1, so this denominator is 1, and if I put n as j here, so this will be simply y dx dz, and because y is 1, so it will be double integral of dx dz only. Okay, so y is 1, and so 1 j dot j is 1 only. Okay, and k dot j is 0. So this is a double integral of the disk, okay, which is a circular disk. So that will be area of unit disk, and we know pi r square with radial 1, so only pi. Okay, so flux through surface S1 is minus pi, flux through surface S2 is plus pi. The total flux will be sum of these two, so that in this case is 0. Okay, so this was one example. Now we come to Stokes theorem, which is a generalization of Green's theorem in plane to space. Okay, so let S be a piecewise smooth oriented surface having a piecewise smooth boundary curve C, and let F be a vector field, which is F is equal to mi plus nj plus pk, where m and p they are continuous first partial, which has components of x, y, z, and having continuous first partial derivatives on an open region containing S. Then we can calculate the circulation of this field around the curve C in the positive direction, which is taken as counterclockwise with respect to the surface unit vector. Okay, normal equals the, and it equals the curl of vector field over the S. Okay, so that means the line integral f dot dr, which is the uh, circulation around the curve, can be calculated as the curl of the vector dot product with the unit normal vector over the surface. Okay, so in Green's theorem we had a curve in plane. Okay, say in the region R, which is lying on the xy plane, so unit normal vector was k. Okay, but now we have a curve in space, so unit normal vector will be n cap, and it will depend on all three components I, j, and k. Okay, so if we assume this to be in plane, then n cap will be k cap, and so this will reduce to the Green's theorem. Okay, uh, so for the general form, the Stokes theorem says that we can calculate the circulation around the curve. Okay, C by calculating the curl of the vector dot product with the unit outward normal, such that the normal vector is the positive direction, or normal vector is chosen so that it is counterclockwise. Okay, so let us say take one example to find the circulation of the vector field. Say vector field is given this x square minus yi plus 4zj plus x square k around the curve C in the plane z is equal to 2 meets the cone at z is equal to x square plus y square root. Okay, counterclockwise as viewed from above. Okay, so the cone in parametric form can be written as r is equal to uh, r cos theta I plus r sin theta j plus r k. Okay, and clearly you can see that radial varies from origin to 2. Okay, and theta for the cone is 0 to 2 pi. Okay, so if you have a cone uh, x square plus y square is equal to 4, which is cut by a plane at height z is equal to 2, so the parametric form of this will be in xy it is polar, and in the z it is a radial vector increasing. Okay, so this is the parametric form. Okay, so from here we can calculate the unit normal vector in the counterclockwise direction seen from above. So unit normal vector will be in the plus direction of z. Okay, so we can calculate it as from the position vector by calculating r derivative with r cross product with r derivative theta and divided by its magnitude. Okay, so r derivative with r is, you can see, cos theta I plus sin theta j plus k. Okay, and r derivative theta is minus r sin theta I plus r cos theta j and plus 0. Okay, and then we can calculate the cross product using the determinant. Okay, so you will find this value, and then magnitude of it will be divided, so that's cos square theta plus sin square theta plus 1 root. Okay, so 1 plus 1 root, that means root 2. Okay, so easily you can calculate this, the unit normal vector, and clearly you can see that the uh, along the z the vector is positive. Okay, so it is in the direction of z here. Okay, so once we have this n cap, we can now calculate the circulation using the Stokes theorem. Okay, by calculating the curl of function, then its dot product with n caps. Okay, so okay, so f vector field is given, so curl of this we can calculate this using the determinant. Okay, so first row is ijk, second row is partial derivatives with x, y and z, and third row are the components of this. Okay, so with I cap we will get uh, y derivative of this minus z derivative of this. So y derivative of x square 0 minus z derivative of 4z is minus 4, so we'll get minus 4i. Then minus j times x derivative of this, which is 2x, so minus 2xj, with z derivative, negative sign z derivative of first component, which is 0, and plus k cap times x derivative of 4z, which is 0, minus the y derivative of this, which is minus 1, so minus into minus 1 plus 1k. Okay, and in the parametric form, x was r cos theta, so immediately we can rewrite this. Okay, and n cap we have, so we can calculate curl of f dot n. Okay, so curl of f dot n will be dot product of these two. Okay, which we can easily calculate. I dot I will be 1, j dot j1 and k dot k1, and the orthogonal dot products will be 0, so we only get 4 cos theta plus 2 r cos theta sin theta, which can be written as r sin 2 theta plus 1 divided by root 2. The ds element will be the in by taking projection on xy, so it will be dx dy by magnitude of n dot k. Okay, so immediately you can see that n dot k will be 1 by root 2. Okay, so if you put 1 by root 2 in the denominator, it will be root 2 dx dy. Okay, so we can now calculate the circulation. F dot dr over c is double integral of curl of f dot n ds over s. Curl of f dot n will be this. Ds element is root 2 dxy, so root 2 will cancel out and we will have this integral with dx dy, and if we convert dx dy to polar, so it will be Jacobian times dr d theta. Okay, so r dr d theta, and the limits of r will be 0 to 2 and theta 0 to 2 pi. Okay, so first we can integrate with r and then with theta. Okay, substitute upper limit minus lower limit. Okay, so you can find that the circulation around the curve c is 4 pi. Okay. The Second theorem is the Gauss Divergence Theorem. Okay, so let F be a vector field whose components have continuous first partial derivatives. Okay, and S be a piecewise smooth oriented closed surface. Okay, the flux of F across the surface in the direction of surface outward unit normal field N equals the triple integral of the divergence of F over the region D enclosed by the surface. Okay, so we already know that double integral F dot N ds is the flux of the field F of passing through these surfaces. Okay, so this theorem says that if your surface S is a closed surface, then we can calculate this flux through the surface by calculating the triple integral over the volume of the surface, triple integral of the divergence of the field over the volume. Okay, so this clearly this theorem is used only for closed surfaces. Okay, and so theorem will not be applicable for open surfaces. So you can apply this for example solid sphere, or where boundary is included, or you can apply it for say a box where all the sides are included. But if you have some box with open top, then you cannot apply this Gauss divergence theorem, because then it will have a open surface. Okay, say for example, say calculate the flux of the vector field this out of the box shaped region D, where box is given by x lying between 0 to 3, y 0 to 2 and z 0 to 1, and use divergence theorem to verify the result. Okay, so we will find flux by the double integral, and then we can also calculate it using divergence theorem to prove that both gives the same value. Okay, only because the box shaped region is closed. You can clearly see the less than equal to sign here, which makes sure that the surfaces are also part of the box. Okay, uh, so the flux of the vector field out of the box shape region will be given by double integral f dot and ds, where s is the surface of the box, and for box we know that there are 6 surfaces. Okay, so if you are given this box with on the x side it is 3 length, with y side it is of length 2, and z height is of 1 unit, then this box has total of six surfaces. So if I rename each surface as s1 s2 s3 up to s6, then the total flux, which is f dot n ds over s, will be sum of flux over the 6 surfaces. Okay, so double integral f dot n ds over s, where s is the sum of all surfaces, will be equal to flux over each of these surface, which is plane x0 x3, plane y0 and plane y2, plane z0 and plane z1. Okay, and so we have to individually calculate the flux on each of them, and then we can add to find the total flux out of box. Okay, and because it is closed, we can also calculate using divergence theorem and prove that both ways you get the same result. Okay, so let us say calculate using one of the surface, say first s1. So consider the top side of the plane. Okay, so this above surface, which is at z is equal to 1 plane. Okay, the unit outward normal you can see will be in the positive direction of z, which is n will be k cap. Okay, so the flux across this side at any point will be f dot n. Okay, so because f field is given, so you can calculate n is k cap, so f dot n will be z e power x. So total flux out of this plane z is equal to 1 will be double integral over s1 f dot n ds1, and f dot n is z e power x. Okay, so dx dy uh, over n dot k, and n is also k, so k dot k is 1. Okay, so z is 1, so we can substitute z1, so it will be double integral of ex dx dy. So integrate with x upper limit minus lower limit, then with y upper limit minus lower limit. So you can see that the flux from the top surface is 2 times e power 3 minus 1. Okay, similarly we can choose other surfaces downward, left, right. Okay, in the xy direction, in the y direction, and we can calculate similarly the n cap f dot n value and then double integral. Okay, so on the surface x0, clearly when x is 0, this back surface, the unit outward normal will be in the negative x direction, so unit outward normal will be minus I cap, and so f dot n value will be minus x square, and because x is 0, so this value will be 0. So flux will be double integral f dot n over that surface, so f dot n is 0, so flux will be 0 on the back surface. Okay, and if we choose the front surface, x is equal to 3, this surface, then the unit outward normal will be in the direction of x, so plus I cap. F dot n will be again minus x square. Okay, now x is 3, so its value is plus 9. So if we double integrate 9 ds, okay, so 9 times the area of this, okay, box with the height 1 and this length 2 units, so it will be 2, so 9 times 2 will be 18. Okay, similarly for y0, so y0 is this back surface here. Okay, unit outward will be minus of j, f dot n with field given is minus 4xyz, with y0 makes this dot product 0, and so if f dot n is 0, the flux will be 0 because it will be double integral of 0 ds. Okay, on surface y is equal to 2, this front surface here, the unit normal will be in the y direction, so plus j. So again f dot n 4xyz with y2 vx 8xz. So now if you integrate double integral 8xz with the x varying from 0 to 3 and z varying from 0 to 1, you integrate it double integral, so it will give this value. Okay, for z0, okay, so base surface, the unit normal will be negative k, the f dot n is z e power x, but with z0 it becomes 0, so flux is 0. And the top surface, which we already calculated, so for z1 unit outward number is k, f dot n is z e power x, z is 1, so simply e power x integrate, so we get this value, okay, which we already solved. So total flux out of this box shaped region will be sum of the flux on individual planes, so we add all these to find the total flux. Okay, so that will be 34 plus 2 e power 3. Okay, now we'll prove that if we use divergence theorem, we'll get the same flux. Okay, so for divergence theorem says that the flux out of surface can be calculated as the triple integral of divergence of field over the volume. Okay, so first we'll calculate divergence of f. Okay, so if you are given this field, divergence of f means x derivative of this, which is 2x plus y derivative. Okay, so it is a dot product. Okay, so 4xz and z derivative of this e power x. So triple integral or divergence f, so that will be triple integral of this, okay, with the z, y and x, and the limits of z, y and x are constants. Okay, so you can use them. So integrate with z first, then integrate with y, and then integrate with x. You see that the result value is same. Okay, so we can calculate easily using Gauss divergence theorem only when the surface is a closed orientable surface. Okay, so we close this topic here. Okay, have a very good day.